The previous videos were on producer optimization. So we asked if the producer has a set budget, what's the most it can possibly produce? But in that case, how do we know that the producer should produce as much as it possibly could? Is there any other profit maximizing output? And then we also talked about the minimization problem, which is if the producer knows what quantity it wants to produce, what is the cheapest way to get there? So in that case, we just set a quantity and said, all right, here's the input combination that results in that quantity at the cheapest cost. But we didn't really talk about how would the producer know exactly what quantity that is that it wants to produce. So this chapter 8, is asking about what is the profit maximizing quantity that a producer can produce or supply. So we're going to start in the case of perfectly competitive markets. It turns out how we find exactly the profit maximizing quantity depends a little bit market by market. We'll start in a perfect competition market, which is kind of the more simple case, and then we'll move on to things like monopoly and oligopoly. So perfectly competitive markets are defined by three basic assumptions. One, price taking. No individual firm has any say over the price in the market. There's product homogeneity, meaning they all produce identical products. And this is sort of why each firm has to be a price taker. All of the products are the same. So if one is more expensive than the other, everybody just buys the cheaper product. Right, so everybody has to stick to the market price. And finally, there's no barriers to entry or exit, free entry or exit, so any firm can enter or leave the market at any time. Right, hopefully you're a little bit familiar with the perfect competition case from 202. There's not really a lot of examples in the real world of perfect competition. It's just sort of a model that we use to start out with, and then we compare others like monopoly and oligopoly to it. All right, so we want to talk about profit maximization, which means we need to define a profit function. So that's what we have here. The profit function, which we will label as pi, is a function of Q, the quantity that we produce. It's going to be our total revenue minus our total cost. Right, so profit equals total revenue minus total cost, and hopefully that kind of makes sense. What's the profit if you're producing? The total amount you got for selling your product minus the total it cost you to produce and sell it. Right, so what is total revenue more particularly? Price times quantity, right? Total revenue is how much we got in total for selling the product. It sold at some market price. We sold some quantity of them, so revenue is price times quantity. You can see that that's a function of Q. And then our cost, our total cost, is equal to also a function of how many we produce, C, or our average total cost, times Q. So total cost is how many did each cost to produce times the quantity that we made. Right, so we often see the profit function written as PQ minus CQ. All right, so here we have some upward sloping cost function like before, and what we're saying about this cost function is just that as output increases, we think that costs eventually are increasing. Now we've got some sort of total revenue function that we think will eventually be decreasing. We can't make infinite revenue forever, although that would be great. And then we can define a profit function, which we're seeing here. And what we're going to show mathematically is that at the maximum point of this profit function, or at the profit maximizing quantity, it turns out that the slope of this total revenue curve is exactly the same as the slope of this total cost curve, or in other words, marginal revenue equals marginal cost. Right, so let's do it, just a reminder, what is marginal revenue? Marginal revenue is the slope of the total revenue curve, or in other words, the derivative of total revenue with respect to Q. How does revenue change when we increase our output or increase quantity? Marginal cost is the derivative of the total cost curve with respect to Q. How does cost change when we increase our quantity. So to show that the slope is equal at the profit max point, or in other words, MR equals MC, we're going to go back to our profit function, and we're going to use the rule from calculus that at the maximizing point of any function, the slope or gradient is 0. Right, and you can look back up here, right, what's the slope at this maximum point? It's 0. Right, so here's our profit function. Profit equals total revenue minus total cost. And we know that maximum exists at the point where the derivative is equal to 0. So we take the derivative of the profit function with respect to Q, and that gives us the derivative of revenue with respect to Q. How does revenue change when we change Q? Minus how does cost change when we change Q? Right, remember from before, the change of our revenue function with respect to Q is marginal revenue, the first derivative with respect to Q. And the first derivative of our cost function with respect to Q is marginal cost. Set equal to 0 because, again, at the maximum, the slope is equal to 0. Right, so we've got here, rearranging marginal revenue equals marginal cost. We can make it a little bit more simple then. We should note that actually this is the profit maximizing point in all types of markets. So when we go on and we look at monopolies, oligopolies, we'll still be using marginal cost equals marginal revenue. And we're actually also going to be assuming pretty similar cost structures across all industries. So suppose we know some sort of total cost function, we can take the derivative of it with respect to Q and get to marginal cost. The only thing that's really going to change industry by industry is how we get to this marginal revenue. So how do we do it in a perfectly competitive industry? Well, we're going to have an industry demand curve which is downward sloping, but the price taker assumption means that any one firm, and remember in perfect competition there's supposed to be many firms, any one firm faces a perfectly elastic demand curve. And what this is saying is just that the firm must charge the market price. If the firm charges a price higher than the market price, then nobody will buy the product for them. Right. As a result of this, for the perfect competitor, we can just say marginal revenue equals price, right? Because, all right, ignore the industry here for a moment. Any individual firm has to sell at the market price. That's the price taking assumption of perfect competition. So if we want to sell one more unit of output, what will be the revenue of the next unit of output? In this case, $4 or market price. And what about if we want to sell one after that? What's the marginal revenue from that next unit of output? Still $4. Right, so again, just to recap, we derived mathematically a sort of informal proof that at the profit maximizing point, marginal revenue equals marginal cost. And what we said is that we're going to assume cost to be the same in all market types, but how we find marginal revenue is going to be different. For the perfect competitor, we have a very simple assumption that marginal revenue equals price. If the perfect competitor wants to sell one more unit, it can do so and always at the market price. Right, so P equals MR for the perfect competitor. And then we can use our optimal condition right here. If we know that P equals MR, then we know that P equals MC. So MR equals MC for the perfect competitor implies P equals MC. There is some set market price. You will find marginal cost from a total cost function, set them equal. In doing so, you can solve for optimal quantity. Right, so there's some math examples out there. I posted another note set which kind of walks through it and does some examples, and then I'll be posting another set of just example problems for this chapter.